Okay, then it's my pleasure to introduce Thomas Walpuski, who moved to Berlin recently and even more recently became a PI in our collaboration. And if there are any questions, please raise your hand and I hope I'll see it or write in the chat.
Okay,
so,
thank you.
Thomas.
Okay, if you write in the chat, I'm trying to monitor it, so I see that as well. Okay, thank you, Sebastian, for the introduction.
I'm trying to monitor it.
Okay, I'll try to talk about something quite concrete, namely how to get more examples of G2 instantons and twisted connected sums. And I'll begin by reviewing how the twisted connected sum construction works. I know that many of you will know how that works, but I need some notation to talk about things properly. So the twisted connected sum construction produces a family of G2 manifolds, which I will denote by Y subscript L. L is some large number, roughly measures the size of some neck parameter. And the input to this construction is a matching pair of framed building blocks. So here by building block, I mean a pair consisting of a smooth projective threefold Z and a projective morphism from that threefold to P1, such that the anticanonical divisor of the projective threefold is primitive. It's sort of multiple of some other divisor, and the fiber at infinity is a smooth K3 surface which lies in the anticanonical divisor. Then a framing on such a building block is a choice of hyperkähler structure, which I encode in terms of the three forms omega I, omega j, omega k on sigma. It's the fiber over infinity, such that the form omega j plus I omega k is of type 2,0. That just means that the complex structure I associated with this hyperkähler structure is the same as the hyperkähler structure that already is the complex structure that already is induced on sigma from Z as a subspace. And then finally, I also need a choice of a Kähler class whose restriction to sigma is precisely omega I. And then we say that these pair of such building blocks, framed building blocks match, or we have a matching. If there's a diffeomorphism R from sigma plus to sigma minus, which pulls back omega I minus to omega j plus, pulls back omega j minus to omega I plus, and it pulls back omega k minus to minus omega k plus. So it flips the complex structures I and j, and it swaps the sign on, consequently has to swap the sign on k. If you have this sort of data, the twisted connected sum construction produces for you a family of G2 manifolds. So one way to get the building blocks is as follows. We take a threefold with a very ample anticanonical bundle. So we take a strong Fano threefold. I'll need that in what I'm going to do. You may be able to do this under much weaker assumptions as well, but then it requires more work. Then by Bertini's theorem, if you take a general anticanonical pencil spanned by divisor sigma 0 and sigma infinity, you can assume that sigma infinity is smooth and that the base locus of this divisor, of this pencil is a smooth curve. If you then blow up the threefold in this smooth curve, you get a new threefold, which is denoted by Z. From the way this threefold was constructed, it inherits a map to P1 defined by the pencil. And together with this map, it forms a building block, and the fiber over infinity is precisely sigma infinity. So now we need to match these things together. Sorry. I wanted to say one more thing. It's important later that in doing this, you can arrange that the fibers only have ordinary double points. This is actually why I want the very ample condition instead of just ample or even something weaker, because I want to make sure that this holds. So now matching pairs of framed building blocks of this kind can be constructed as follows. You choose a pair of lattices, n plus and n minus. And then for each of these lattices, you choose a deformation type of pairs WH, where H is a strong Fano threefold, W is a strong Fano threefold, and H is an isometry between the lattice n plus or n minus and the Picard lattice of the Fano threefold. And then you choose an open cone in the vector space associated to the lattice n plus or n minus. Let's call these open cones amp plus and amp minus, such that the following holds. Whenever you have a pair WH in the deformation types that you choose, the image of amp plus minus under H lies in the ample cone of W. So we know all of the deformation types of strong Fano threefolds, even Fano threefolds. These lattices that are associated with this can be computed, and you can also work out reasonably large portions of the generic ample cone and use that for amp. Okay, suppose you have that, then you choose a further primitive sublattice that lies within n plus and n minus, and you assume that there's an orthogonal push out of n plus and n minus along n0. Let's call it push out n. What this means is that n plus and n minus both are sublattices or embedded in n. They span the lattice n, they intersect precisely in n0, and the perpendicular of n plus, respectively n minus, is a subset of n minus or n plus. You can always construct this push out rationally, so you get a lattice that takes rational, where the intersection point has rational values, and that's unique such thing. Then you can check if that actually takes integer values. If it does, this orthogonal push out exists. So this, whether or not this push out exists, is completely computational. It's easy to check computationally. And the last thing you do is you suppose that n is primitively embedded into the K3 lattice. By a theorem of Nikulin, you can always do that if the rank of n is sufficiently small. So this is an arithmetic situation. It only depends on the choice of lattices. And if you can arrange that, we have the following theorem that's due to Kovalev and Corti, Haskins, Nordström, and Pacini, which has the following. Suppose you have found H plus and H minus in the intersection of M plus, respectively amp minus, with the perpendicular of N0, and you fixed some number, epsilon, should be thought of as small. If this H plus minus is, can be chosen and epsilon is whatever you want, then you can find the pair W plus minus H plus minus in these chosen deformation types. Within W plus minus, you can find a smooth anticanonical divisor sigma plus minus. You can put a hyperkähler structure on this divisor, and you can find a suitable hyperkähler rotation, which has some compatibility conditions with H plus and H minus. And then also important for us will be that you can arrange that the chosen H plus minus is at most at epsilon distance from the omega I plus minus in the hyperkähler structure. So once you have the output from this theorem, what you do is you take a second anticanonical divisor in general position in both W plus and W minus. You blow up the base locus of the corresponding pencil, and that gives you building blocks, as I explained before. And the hyperkähler rotation is the required matching data. Okay, so this is how you construct twistor-connected sums that will be relevant for this talk. Now, I'll briefly explain how you can construct G2 instantons on twistor-connected sums. A while ago, Henrique Saeb and I, we proved the gluing theorem, which takes the following input. So first of all, you start with all of the data you need to build a twistor-connected sum. So you start with a matched pair of framed building blocks. On each of the building blocks, you choose a holomorphic vector bundle of rank R, but they're both of the same rank. That's important. You assume that when you restrict these bundles to the divisor at infinity, that they're both mu stable with respect to omega I plus minus. Then result of Donaldson tells you that there's a corresponding ASD instanton on the underlying topological bundle, which I denote by A infinity plus minus. Then there's a matching condition which says that we require to have an isomorphism of the smooth vector bundles E plus and E minus restricted to sigma plus minus, which covers the hyperkähler rotation and pulls back the corresponding ASD instantons to each other. That's sort of a matching condition at infinity. The third condition is that it's impossible to deform E plus minus infinitesimally without deforming the restriction of E plus minus to the divisor at infinity. This is encoded in this cohomological condition. And then there's a fourth transverse intersection condition, which is a little bit too complicated to explain in the time frame that I have. You can look it up in the paper that I wrote with Henrike. I will later, if I get to it, talk about the case where this becomes a very concrete intersection condition that has a very clear geometric meaning. In any case, if you can satisfy these conditions, then out of this data, I can, or Henrike and I, we can construct for you a G2 instanton on the submanifold, the manifold YL that comes out of the crystal sum construction, and has some properties. It's unobstructed, it's irreducible, and it lives on the PUR bundle. Okay. So this theorem is quite difficult to use because conditions 2 and 3 would leave the realm of algebraic geometry. And condition 4, as I said, is even a little bit complicated to even formulate. There's a simpler case, the rigid case of this theorem, which you can obtain by combining a result of Donaldson and Mukai with the theorem, the gluing theorem. And you have the same situation as before. You have this matching pair of frame building blocks. You have a pair of holomorphic vector bundles, but now you impose stronger conditions. So again, you want them to be mu stable when restricted to divisor at infinity. But then sort of the matching condition, you can require it as a much weaker condition that only the first and the second Chern class match under the hyperkähler rotation. So that's easy to check, easy to set up. And the third condition is that both E plus minus and its restriction to the divisor at infinity is infinitesimally rigid, which is encoded in this cohomological condition. And all of these conditions are much easier to check. In particular, they don't leave the realm of algebraic geometry, or complex algebraic geometry at least. And in this case, you also get an unobstructed irreducible G2 instanton on YL, constructed out of E plus and E minus. So it turns out that if you look at the literature today, you will find precisely 2 examples of G2 instantons constructed using this gluing theorem. The first one I constructed a few years ago using the rigid case on a twist sum that was discovered by Crowley and Nordström. And then more recently, Menet, Nordström, and Saeb managed to construct G2 instanton using the gluing theorem on the previous slide, which does not fall in this rigid case. Okay. So now the question is, how do you get the input for these gluing theorems? And then what I will tell you is that you can actually find this input in many cases. So it's quite useful to sort of take a slightly different perspective on this input. I mean, it's just change of perspective. It doesn't fundamentally change what you're looking for. You fix some essentially topological data. You fix a number R, which denotes the rank of the bundle. You fix a class B and N0 in this lattice N0 that I was talking about before. And you fix a number S, which can be any integer. And these 3 things together are denoted as this vector V. Then we choose H plus minus as before. And now you consider the relative moduli problem of sheaves over the building block, which this building block is, these building blocks are K3 fibrations. You can consider the relative moduli space of bundle problem of sheaves, which have this given Mukai vector, which means that the rank of this bundle when restricted to the fiber is R, its first Chern class is B, and its Euler characteristic is R plus S. And it's important that these moduli problems have a fine moduli space. You need to impose some condition. I will always impose Giesecke stability with respect to H plus or H minus. And this fine modular space exists under the assumption that R and S are co-prime. So this will be something that has to be assumed from here on. If you have this, then the conditions of the gluing theorem, they can be translated to conditions on sections of M plus and M minus. So every section of M plus or M minus gives you a sheaf over Z plus or Z minus just by pulling back the universal sheaf. And conditions of the gluing theorem translate to the following. So first of all, you need that the value of S plus or S minus over infinity represents a new stable bundle that gives you corresponding ASD instanton, and you have the same matching condition that when you pull back the ASD instanton A infinity minus, you get something that's gauge equivalent to A infinity plus. We don't need to worry about providing, first of all, an isomorphism of the underlying vector bundles that's automatic by the choice of these Mukai vectors. Then you need to know that the value of S plus minus at every point represents a vector bundle. You need this to know that the pullback of the universal sheaf actually gives you a vector bundle over Z plus minus and not something more singular. Then you have this condition that S plus and S minus cannot be infinitesimally deformed without deforming its value at infinity. That also has a cohomological version, but I'm not going to write that. And there's a transverse intersection condition, which again, I won't write. So the strategy then is to try to find cases where the moduli space M plus and M minus is very simple. And simply based on that, you can find examples. Okay. So an important invariant of this moduli space is its expected, but in the cases, I would consider the actual relative dimension. This is always given by 2 plus V squared with respect to quadratic form that was introduced by Mukai. If you write that out, it means that the relative dimension is 2 plus V squared minus 2RS. So the simplest cases you can consider are relative dimension 0 and relative dimension 2. And it turns out that based on the work of Kuleshov, Mukai, Thomas, Bridget Makiokia, and many other people, in these cases, you can understand what these moduli spaces are reasonably well. Again, you have to assume in this theorem that the fibers of the building blocks only have at worst rational double point singularities. But if you know that, and you know that the relative dimension of the moduli space is 0, and R and S are co-prime, we need that for the moduli space to exist, then we know exactly what M plus and M minus is, namely it's just P1. So over every fiber, there's a unique vector bundle with the given Mukai vector. And it only parameterizes vector bundles. Nothing in this moduli space has singularities. If the relative dimension is 2, which means that V squared is equal to 0, and again, we assume that R and S are co-prime, then you know that M plus minus is now a building block. And you know that if you have a point on M plus minus, which is the smooth point of the fiber, it corresponds to a vector bundle. If it corresponds to if it's a singular point in its fiber, it parameterizes a reflexive sheaf, which is not smooth. So an actual reflexive sheaf. And one can be more precise about describing that, but won't be necessary. And then finally, we need some condition that guarantees, so these are all moduli spaces of Giesecke stable bundles. But we need this hypothesis that over the fiber at infinity, the bundle is actually mu stable. So you need some condition to impose which guarantees that Giesecke stable bundles actually are mu stable. And the usual way to do that for algebraic geometers is to suppose that the rank and degree are co-prime, but the situation that we consider forces the degree to be 0. So you cannot use this condition. You have to use this slightly more annoying condition, which is the following. So if you have a U semi-stable bundle with respect to H on a K3 surface, and it has Mukai vector V, and you know that R and the divisibility of B as a homology class are co-prime, and you also know that every element X in H11 of the K3 surface, which is perpendicular to H, has a very negative square, so it satisfies this inequality here. X squared is less than or equal to -1/4 R squared times, and then in parentheses 2 times R squared plus V squared. If you have this inequality, then the semi-stable bundle must actually be stable. So if you combine this theorem of the theorem that I mentioned in the proposition that I wrote here, you get the following corollary. So in the situation considered before, where you have these lattices, the orthogonal pushout, the deformation type, amp plus minus, and so on, and you have found H plus minus in amp plus minus intersect N0 perp, and you found the Mukai vector such that the following conditions hold. First of all, you want that the Mukai vector squares to -2, corresponds to B squared is equal to 2 times RS minus 1. You impose that the divisibility of B and R are co-prime, and also that R and S are co-prime. So these are easy to check and easy to arrange. And you impose this condition, which is needed for mu semi-stability to be the same as mu stability. You impose that every element X in N plus minus, which is perpendicular to H plus minus, has square less than -1/2 R squared times R squared minus 1. If you can find situations where this holds, then using the theorem of Kovalev, Corti, Haskins, Notcham, and Pacini, you'll find a matched pair of framed building blocks, and using the rigid case of the gluing theorem, you can find the input for the rigid case of the gluing theorem and construct the required G2 instantons. So the important thing about the hypothesis of this corollary is that they're in essence completely arithmetic. Once this initial data is fixed, finding the Mukai vectors in H plus minus is a completely arithmetic condition, or checking whether this satisfies a completely arithmetic condition. And it's something that you can brute force search for on a computer. So if you first sit down and look at all of the strong Fano threefolds, you compute the Picard letters and you find a good choice for amp plus minus for the strong Fano threefolds, then you can simply do the following. First of all, you choose a Mukai vector which squares to -2, such that R and the divisibility of B are co-prime, and also R and S are co-prime. That's easy to do. Then you check if you can construct a push out of N plus and then minus along the lattice N0 spanned by just B. And if you can do that, then finally you try to find H plus minus in M plus minus intersect the perpendicular of N0, such that condition star from the previous slide holds. This is also, again, something you can check. I've done this for the Fano threefolds of rank at most 3. And you can let my computer search for examples, and I found I found exactly 299 new examples in 3 days. And here's some statistics of the results of the examples I found. One of the examples is not new, it's the one I constructed using on the Twist-connected sum found by Crawley and Nordström, that has rank 1 or rank 2. All of the other examples, the Henrike, the example by Menet, Nordström, and SEP also is a rank 2 example. I found 23 more rank 2 examples. And then I found more examples with higher rank. And in particular, I found a lot of examples with rank 7, which I find is a curious coincidence. Initially, you can believe that maybe this is because you just rediscovered the Levi-Civita instanton on these twist-connected sums, but the Levi-Civita instanton cannot come out of the gluing construction because it's not going to be unobstructed. If you want to see more details, you can look at I have not on the archive, but preprint on my webpage, where you can find exactly which matching pairs give instantons, and you can see some statistics and diagrams there. There's also the code you can look at if you want to run this yourself. Anyway, so these, so what I'm saying here is that there are a lot of new examples of G2 instantons. It's not just two. And then, how much time do I have left? I have 4 minutes left, is that right?
Maybe -1, because the talk was 25 minutes, wasn't it?
Okay.
But if you have just a few sentences to say, I think that's fine.
No, if I have no time left, then I'll stop here.
No, I think it's fine. Most of the talks, right? We give people the, I'm sorry to interject, but if you want to comfortably conclude, right, please do so.
Let me do one more slide, and then I have 3 more.
Yeah, very good.
Let's do one more because it has all of the main things anyway. So you can also try to figure out the case when v squared is equal to 0. The ideal situation that you can arrange is that you have that the moduli space, the relative moduli space, actually is identical to the building block, and that the fiber over infinity parameterizes only mu stable bundles. The last condition is easy to arrange. The first was a little more tricky. If you can do that, then by the way that the building block is constructed, you know that the building block itself actually has a lot of sections, holomorphic sections, that come from points of the base locus. And the transversality and matching conditions exactly translate into the base locus on one side to transversely intersect the base locus on the other side in a given point after you apply this hyperkiller rotation. So every point, transverse intersection point of the image of the hyperkiller rotation of C plus and C minus gives you a G2 instanton. And you can, these things, if you can arrange this hypothesis at the beginning that M plus equal to plus minus equal to Z plus minus, then you can get a lot of G2 instantons from this. Okay, so the same pair of sections also gives you an associative. So this is sort of a situation where you have two G2 manifolds which are self-dual to each other in a certain way. So the question is whether you can actually arrange this condition. There's a theorem of Nikulin and also I think of Nikulin and Madonna that sort of gives more details on this, that tells you under certain conditions on the Mukai vector, the smooth fibers of M plus and M minus are isomorphic to the smooth fibers of Z plus and Z minus. In some cases, these isomorphisms that Nikulin describes that Nikulin defines, they can be described geometrically, for example, using the Serre correspondence and various constructions of holomorphic vector bundles. It was worked out by Turin in some cases. And in those cases, you could make sure that these isomorphisms globalize. But in general, the missing thing to actually make this work is to figure out when this Nikulin isomorphism can be made global. So not just to have a fiber-wise isomorphism, but actually an isomorphism of the whole moduli space with the building block. If you can do that, it's not that difficult to find the corresponding examples of these Mukai vectors in the matchings that would give you examples for this, but this is something that's missing. Okay, then I'll stop here. Thank you.
Yeah, thanks for the nice talk. And again, if you have questions, please raise your hand.
Dave has a question.
Oh, yeah.
Yeah, I was curious, can you relax the condition on G2 instanton to be a sheaf instead of a bundle and maybe use those singular points in moduli space to some good effect?
So, okay, I forgot. So these sections never see the singular points in the fibers because the section cannot go through the singular point in the fiber. There might be an analog of these. So we know that reflexive sheaves would give you singular Hermitian-Mills connections, and you could try to glue them together on the corresponding things. The gluing theorem for that, I think, is not worked out. It's possible that Yuanji Wang is going to talk about some aspects of this on Friday in the discussion section. But these reflexive sheaves, I think you don't see from these relative modular spaces that are building blocks themselves. You have to go to Mukai vectors that have larger squares.
I see, thanks.
Any further questions? Yeah, Dominic.
Is it possible that you might produce an infinite number of examples in this way?
I don't think so. I don't think so, because oh, you mean without any restriction on the rank? That might be possible. Yes, if you don't impose the restriction on the rank, I don't see why it would be impossible. If you restrict the rank, I think it's just, you can derive an extremely bad upper bound on how many you could find.
Where does the restriction on the rank come from?
The restriction on the rank. Well, I mean, you might, are you asking where it comes from or how you would use it?
Yeah, where does it come from? Because I couldn't see that.
Oh, there's no reason to assume if you don't assume a restriction on the rank, I don't know if you could potentially produce infinitely many. I'm not sure.
You could probably just tensor examples together, couldn't you?
Sorry, say it again. Oh yeah, of course you can do things where you try to construct reducible connections. If you're happy with reducible connections, you get infinitely many, but that's not interesting, I think. Is that what you mean? What you were talking about?
I mean tensoring rather than direct sums. But
yes, yes, okay, yeah, or you can do that, but that may then split. They may split into. That's a good question, actually. What happens? You keep tensoring them. If they, at some point, they split into things you've already seen.
Well, then you'll get a ring. So you can ask whether that ring is finite type.
Yeah. Yeah, that's a good question. These are actually good questions, but I don't actually think that they're strictly related to this. You can consider this for any G2 instanton, any G2 manifold. You can look at G2 instantons and look at the ring generated by tensor products and direct sums.
Is it straightforward to compute the second Chern character of these bundles and compare it to the first Pontryagin number of Y?
Yeah, you can relatively concretely describe what the first and the second Chern class are of these bundles, and from this you should be able to compute. In the same way that in Corti-Hessrin's Notrumi Pacini, the Pontryagin classes worked out the same construction, the same kind of work that you have to do to work out the second Chern class of these bundles. Yeah, that should be possible. Yeah.
In the world of G2 instantons, we expect to attach signs to them if they're isolated rigid.
That's right. Yeah.
Do you see signs in your construction? Is there somewhere?
So, no, I don't see an obvious way where sort of a canonical choice of sign enters, but it's a good question.
So I have another, maybe more of a comment than a question. But there's a big world of DT theory, counting bundles and sheaves and so on Calabi-Yau threefolds. There ought to be a relative version of that where you would count, just in algebraic geometry, where the count would take values in something like the homology of the moduli space of bundles over the K3. Something of that kind. So it would be essentially roughly you'd have your moduli space of bundles on the Fano, restricts to the moduli space in the K3, and that would have a homology class.
Yes.
But I'm wondering whether that theory has been developed. Maybe Dominic knows about that.
Not by me.
No. But if, let's say, supposing it was, then at least ignoring some technicalities, you could compute numbers by just using intersection theory and the homology of the moduli space of the K3s.
Yeah. If there are no more questions, maybe we just.
Yes, can I ask a question, please?
Ah, yeah, okay, of course.
Got a raised hand thingy. I don't know if I've done it right. Sorry.
Ah, oh, you did?
So Thomas, I was under the impression from halfway through the talk that you were always making the asymptotically rigid assumption, right? There are no.
Oh, yeah.
Right? Is that the case? But then the second paragraph,
the last slide here does not. The last slide and the two slides following would not make the rigid hypothesis.
So then
this is how I think about half of your construction with Johannes and Grégoire, because half of the data in your construction comes from this. It comes from exactly a case where the moduli spaces, or the relevant part of the relative moduli space, looks exactly like Z plus minus, and you can see that from the SER correspondence that you use.
Yes.
But the other half does not come from this. That I actually found that a little bit surprising.
My other half, it's completely ad hoc. You just have to make things match.
Right.
Yeah. So that's why I was asking. So among the examples the new examples you compute, there's lots of them. It's amazing, right? It's many more than we knew before. Do some of them have then non-trivial transverse intersection?
No, not yet. Not yet. I'm still working. I mean, I'm not that actively working on this project actually, but when I get back to it, I'll try to find some non-rigid ones. Yeah.
Do you think that would still be a case for the SER construction, or is it? One could try and.
So I mean, so the Nikulin gives this isomorphism. You can basically determine the period point that corresponds to the fibers of M plus and minus, and from that you can deduce that there has to be an isomorphism sometimes. That's what Nikulin does. You can sometimes explain this from the SER construction, right? But that doesn't explain everything. But there's more than a SER construction you can do. You can do a SER construction. You can twist by further bundles. You can do this operation called the Mukai reflection, and some other constructions. And they explain some of the Nikulin isomorphisms, but I don't think they always explain everything. So it could be that if you use more than just a SER construction or a relative SER construction like you do, you can find more examples like you did with Henrike and Grégoire. Sorry, with Johannes and Grégoire, but I haven't tried that yet. Right. I can send you this paper of Thury and you can take a look, and Nikulin, you can take a look, see if that.
Please. I'm touching Grégoire again, so we are going to look into this, and now we're probably going to have to read this thing in a lot more detail. Have a look. Yeah, thanks.
Yeah, okay. Sorry, I didn't see the raised hand, so we know now that the raised hand doesn't automatically put yourself up on the list. Yeah, oh, sorry for that. So any more questions? Then I think the idea is to go over to the discussion.